So the topic of my talk is parametric estimation of stochastic volatility models. So stochastic volatility model and in general stochastic differential equations have been sort of ubiquitous in the area of quantitative finance. These are equations which are heavily used to model various financial time series, be it the stock price, interest rates, and so on. So one of the key issues, of course, is to select the right kind of model which captures all the features that are observed in the empirical data. So it is crucial that the selection is based on some sort of justification and good amount of statistical basis for the choice of the model. So the context in which I will be sort of studying the estimation is a general framework that we have proposed here. So the general framework is really that of indirect observability. So that's the key word that we have proposed. The main objective here, so let me start by the steps or giving you the outline of this study. So the idea is that there are the first equation that you see, that is a stochastic differential equation. So people who are sort of aware of this topic will know that differential equation is really a misnomer here. This equation needs to be interpreted, in fact, as a stochastic integral equation. Here the W represents Brownian motion, a standard Brownian motion. So this is a good tool to model financial time series, as I said. The problem that we are trying to study is, once you set up this model that you believe that your data follows, how do we calibrate this unknown parameter theta which characterizes this stochastic process? Now, classically, this problem of estimation has been solved when your observables. So another point that I would make before defining the observability criteria is that, so that is a model which is a continuous time model. But what you have available are discrete observations, denoted here by UN, which have been sampled from this continuous time at some discrete time steps with just spaced at delta unit. Okay? So the first point that you sample is time 0, delta 2, delta 3, delta, and so on. So you have these discrete observations available to you. What is then the methodology to estimate the parameter theta? Now, as I was saying, classically this problem has been solved when your observations, denoted here by UN, are directly observed from the process X, which is being estimated. Okay, parameters of which are being estimated. So that is to say, the equation that you are estimating and the data are sort of consistent. But this is not the case typically in real world, right? The data generating machine is not this model. This model is only a representation or an approximation to the reality. Okay? So it is sort of the ideal case that your data and your model would match, statistically speaking would match. Okay? So the indirect observability, which happens to appear in a lot of cases, I will motivate this with certain examples. The indirect observability has been defined in the following manner, that your discrete observations on the basis of which you would estimate your parameters are being sampled from some approximating process. Okay, let's call that process y epsilon. So there is some index by some small parameter epsilon, and as epsilon goes to 0, this process y, which is our observable process, is limiting or converging to the true process xt, which is unobservable. Okay? So, of course, I will state in the problem or in the general framework in which we study what is this convergence, in what sense is this convergence true. Okay? So, just that indirect observability is the case when there is some sort of a discrepancy between the data and your model. The main objective of our study is to look at the asymptotic properties of the estimators that we derive, and also in a real scenario, what are the subsampling conditions or the subsampling criteria? At what frequency should I sample my data? What should be my delta so that I can reduce my bias in the case of indirect observability. So, to statisticians, some of this is going to be very counterintuitive. I think when I motivate this with an example, that's the time when I will state what is that counterintuitive notion here. Alright, so the framework that I just defined is a very general framework. I said there is approximating process converging to the process X, but what are the other conditions that I need to impose so that I can derive certain good estimators? Okay? So this is my sort of most general framework that we have devised so far. The following is the hypothesis on the unobservable process X. X is a centered stationary Gaussian process. So Gaussian because it allows us to compute a lot of these L2 norms, L3 norms in closed form. So it's an assumption which we sort of work with. And then we have this covariance function, okay, denoted here by Ku. So the covariance at some lag u is nothing but the expectations of this product xt plus 2. So it's like the correlation on the covariance function is just capturing my covariances in the process at some lag u. Okay, since it is stationary, notice that the covariance function is independent of t. Okay? A couple of other assumptions or hypotheses that I need to put in is the following. The covariance function is assumed to be piecewise C1, so continuous derivatives in u and in theta. And the following condition, that I need my covariance function to decay exponentially in the lag. Okay? So this condition actually just captures that. The last condition is sort of a corollary to the hypothesis that we set up. But the idea is that these conditions should allow me to select certain finite number of lags u1, u2 to up, okay, such that I can sort of set up some system of equations or moment conditions. So these are basically just moment conditions. My covariance at different lags are equal to some scalars. Okay. Now the idea behind, this is sort of a method of moment in estimation. That now, if I'm able to represent my unknown vector parameter theta in terms of these moments, then as long as I can estimate these moments in a consistent manner, then I can say something about the consistency of the parameters estimates for theta. Okay, so this is why this condition is important. So I'm sort of masking a couple of other regularity conditions here, but given the setup, I can represent my vector theta in terms of these moments. Okay. Now, because this is an indirect observability framework, I need to set up some hypothesis on the approximating process y epsilon. So y epsilon is the process on the basis of which I will estimate my parameters theta, which actually characterize the unobservable process xt. Hypothesis of y epsilon is that it's a centered stationary process, so it can have arbitrary probability distribution, so no assumption on the distributional aspect of it. And then that yp epsilon converges to xt in the N4 norm. Okay? With the order of convergence or the speed of convergence sort of captured by this rho epsilon, which as epsilon goes to 0 will converge to 0. So this is the sense in which my process converges to a true process. My approximating process converges to a true process. In addition to that, I have this sort of a uniform bound in L4 norm for the process yp epsilon. Now, I stated this multiple times, the objective is to obtain consistent estimators for the unknown vector of parameter theta based on the observations from the process y epsilon. Right. Now, as I stated, so recall that, let me actually just put it down just for recollection. So theta is, so I'm able to represent my vector theta as this function of r, so it's a multi-dimensional, p-dimensional function. So I select some finite number of lags, and I have these moment conditions. converting the system of equations, given that the Jacobian is certain condition of the Jacobian, I can state that. Now, let's see how do I set up the consistent estimators for my covariance. So let's say covariance at some fixed lag u can be, in a very straightforward manner, can be seen as so this empirical or the sample estimate, which is nothing but given n plus k observation of my data from the process y epsilon. I just define these sample estimates, which are nothing but the product of y n delta and y n plus k delta, where k delta is u. So I'm just looking at the covariance or the empirical estimates of the covariance at lag u. Okay? Now notice that here I'm sort of suppressing the dependency on epsilon, but this is dependent on epsilon because the process is indexed, the observable process is indexed by epsilon. So under the following hypothesis, so as epsilon goes to 0, if I have more number of observations and so here this k epsilon is basically defined in the following manner, that k delta equals u. So I need k epsilon going to infinity at a much slower rate than n epsilon, such that the delta or the sampling time step length is chosen to be u by k epsilon. That's sort of obvious because I'm estimating the lag at u. Then I can prove that the covariance estimators based on the approximating process converge to the true covariance at lag u. Okay? In particular, we can sort of derive these bounds on the L2 norm for these covariance estimates. Okay? Now that I have that in place, it's sort of an easy extension to state that parameter estimates for theta, which are defined to be this f of the moment estimators, would also converge, at least in probability, as epsilon goes to 0, and the conditions that I defined for the asymptotic conditions are defined for the n, k, and delta. Okay? So, any questions so far?
Are you assuming x and y are geometry stationary?
No.
Because your quantity like yt minus x, yt epsilon minus xt, that doesn't depend on the L4 norm. The L4 norm of plants.
The L4 norm of
yt epsilon minus xt.
Correct.
So you're assuming it's independent of t or not?
It is independent.
So it's geometry stationary.
Okay.
But this exposes is governed by why is it there? I think that no, X. I think it's an experiment.
Alright, so that is the general framework which has been defined to study the indirect observability context. Now let's look at a couple of specific examples. Apologies, I'm not yet arrived at the stochastic volatility models because I just want to motivate the problem a little bit better. So let's consider this sort of a prototypical model that we have considered here. It's a stochastic differential equation known as the Ornstein-Lundbeck process. So the stochastic process satisfying this differential equation is Gaussian and is stationary. So it sort of fits in very well in our general framework. Again, here the objective is to estimate parameters lambda and sigma based on an approximating process. Now, the approximating process that we consider here is the following. What we've done is that we have this stochastic process, the Ornstein-Lundbeck process, whose dynamics are represented by the differential equation that I had in the previous slide, and we just do a sort of a local averaging of it. So we call it the smoothed Ornstein-Lundbeck process. So we are locally smoothing the OU process on some window of length epsilon
YT epsilon that
I'm sorry?
your YT epsilon that
Is
observable.
is observable. Correct. Yeah. So I'm just setting up a sort of toy example here where I assume that my observables come from this process YT epsilon. Right? And here the YT epsilon can be shown to converge to XT in L2 norm. Both these processes are Gaussian, so I can compute exactly these L2 norms and can show that the convergence holds. And then I sort of step 2, doing some experimental study, or only experimental study. Here things can be calculated exactly. But the idea that I'm trying to convey is what would happen, what would be the asymptotic properties of the estimators lambda and sigma in the previous equation if I base their estimation on process YT epsilon, which is my smoothed OU process. Okay? So YT epsilon is zero mean stationary Gaussian process. We can show that very easily. So I think I'll just sort of take a pause here and dwell on something very important here. The OU process is a stochastic process where the trajectories are, there is certain amount of noise in the trajectories, right? Whereas the smoothed OU process, although a stochastic process, the trajectories are differentiable. Okay, so these are smooth trajectories, right? Now, if I'm basing the estimation of a certain process which is fundamentally or trajectorially different, then it is sort of an obvious fact that I would not get back my parameters. And when would I not get back my parameters? If I'm sampling very frequently, if I'm taking high frequency data from my smoothed OU process, and I'm sort of putting that data into or calibrating my OU process to that data, then there is a difference in the small scale properties of these models. Does that make sense? Right, so these two processes are fundamentally different. The trajectories for the smoothed OU process are differentiable, okay? Whereas the trajectories for the OU process are not differentiable. There is noise in that. Anyway, so let's move forward. All right, now there is a very interesting result that Yaglo, YAGLN, had proved in the 50s. That is to connect the differentiability of the covariance function at lag 0 to the differentiability of the stochastic processes. Okay, so it can be shown that if my covariance function is differentiable at lag 0 once, then the stochastic process, or rather twice, if it's twice differentiable, then the stochastic process is differentiable in a mean square sense. So there is, it's sort of differentiable in the L2 norm, that there is a derivative with, a derivative process, so to say, which such that the L2 norm the difference would converge to 0. So, which is interesting, which is sort of what is, sort of what is the key here, because the estimators, the theta, the parameter theta, or in our case the lambda and the sigma, the way they are estimated are from the moment condition. So they depend on what the covariances are at lags close to 0. Okay? I'll just sort of explain that a bit more in detail in the next slide. But this is just to sort of dwell on this, that the covariance function for the OU process is in fact not differentiable at lag 0, whereas the smoothed OU process, again, we can exactly compute what the covariance function is, and this is, it's sort of concave down at lag 0, and it's differentiable at lag 0. You can show that it's twice differentiable in fact. Estimation problem, stated it, but we have n discrete observations sampled from the smoothed OU process. The parameter estimators for the lambda and the sigma are some functions of the data and the estimation parameters n and delta. So you have n number of observations which have been sampled at length delta. Okay, so the question that we're trying to answer is what is the asymptotic consistency, what are the conditions under which these parameter estimators are going to be asymptotically consistent. Of course, the general framework answers that. Here, we can do a little bit more. The general framework gives us the upper bounds on those norms, but here we can exactly compute. Just to sort of go a little bit deeper into the expressions here. So the lambda parameter, the estimator for that is this negative 1 over delta log of R1 by R0. So R1 is the covariance at lag delta, and R0 is nothing but the variance estimate, which is just the sample variance and the sample covariance. So represented by these two expressions here. Okay, so R1 is just the covariance estimated from the data of lag delta and variance estimated. Okay. Now again, sort of in the direct observability case, that is if these observations were coming directly from the process X, it's sort of classical problem, and it has been shown that these converge at a rate of 1 over square root n delta. But in this case, we sort of extended that to the case of indirect observability, where we show that under the following sort of subsampling conditions, let's call them subsampling conditions, that as epsilon goes to 0, delta goes to 0, and my observation time n delta goes to infinity. I'm observing the process on a longer and longer time interval. And additionally, this delta over epsilon converging to infinity. This is sort of the key condition here, which captures the bias due to the indirect observability. So this is what I was talking about. That if I'm taking my observations from the process smooth OD process, which has continuous trajectory, I cannot sample very close. I mean, I can't sample high frequency because then my bias is very high. Again, I'll give you the expansion and probably that will make it further. So under these conditions, we can show that the parameter estimators are actually L2 consistent. Moreover, under some additional conditions, we can even show that the speed of emergence of 1 over square root n delta is achievable, which is sort of the classical case.
The sampling gaps are delta.
Correct, the sampling gaps are delta.
Then you want after delta to go with
Go to infinity. Correct. So that is required for consistent estimation of the variance, I mean the volatility parameter. Correct. So delta and epsilon both go to 0, but delta should go to 0 at a much slower rate than epsilon. You don't want to see sort of too granular in this approximating process, because the approximating process and the true unobservable process differed in the small time, I mean, in the small scale properties. I mean, that's where the difference is at. Okay, so what's sort of the interpretation? What could be the numerical recipe that we can provide based on that previous theorem? It's the following. One thing that we can sort of derive is that we can derive the following asymptotic expansion for the parameter estimator. So gamma, the estimate of gamma has this bias, which is due to finite sample and discrete samples, so sort of the classical term, 1 over square root n delta. But additionally, it has this bias of epsilon over delta. Okay. Now, notice that in reality, you have one set of data which has been generated with some epsilon, which is again unknown to us. Right. Now, for that unknown epsilon, the bias here is still of the order epsilon over delta. But if I reduce my delta, if the fact that the observations are in fact coming from approximating process is not known to me, then again classical statistics will tell me that more the data, better placed I am in estimating my parameters. So I would go about collecting data at much finer delta, much smaller delta. And what that does is it blows up the errors in my estimates. Okay? So it blows up like 1 over delta. So, okay, so what is the optimum subsampling criteria of conditions? So as epsilon goes to 0, if I choose my n as epsilon to the power negative eta and delta to be epsilon to the power alpha, then I need that alpha should be between 0, 1, so that the condition, so that bias epsilon over delta converges to 0, and that eta has to be greater than alpha, so that n times delta, the n times delta converges to infinity. So that these conditions, which can then be numerically tested, and that's why we derived these conditions, and that leads to consistency. And some additional conditions will lead to the relative speed of convergence being 1 over square root n delta. Alright, so it's just some numerical results. Of course, in this particular case, we've been able to compute everything analytically, but just to sort of highlight a couple of things here. Now, this delta is chosen to be epsilon to the power 0.5. So as epsilon goes to 0, my delta is also converting to 0, but only at a slower pace, slower rate. Then I see that I'm in the sort of the consistent regime or the good regime. In that case, my errors converge to 0. So on this axis I have the errors, and on this axis I have the epsilon. In the case when delta equals epsilon, sort of the boundary case, here, if you recall from the expansion, if delta equals epsilon, I'm making an order 1 error. Okay, so that is what we observe here. The errors converge to some sort of finite error. Okay. And the case when delta equals epsilon squared, my delta is converging to 0 at a much faster rate than epsilon as epsilon goes to 0. In this case, my errors actually just blow up. So that's the scenario. Now, so this is the problem, or problems of this class is what motivated us to sort of look at this problem or consider this study. So here, I'm not going to go through the details because I really want to get to the stochastic volatility model. But here, what you see is a multi-scale system. So this is a 3-dimensional stochastic differential equation, a system of stochastic differential equation, which evolved. These two variables are sort of the fast variables. They evolve on a much faster time scale, whereas the process X evolves on a much smaller or much slower time scale. Okay? So there is theory, stochastic mode reduction, which gives us that as the parameter epsilon, which is sort of the time scale, which captures the time scale separation, as that converges to 0, the slow variable, so let me just sort of motivate. So these kind of systems arise in atmosphere, ocean, in climate models. The X could be representing really the climate pattern which evolves on a much slower time scale over decades, and these could be sort of more localized weather patterns or ocean patterns which evolve on a much faster time scale. So the interest is more in studying how, what are the statistical properties of these slow variables. But if you were to study this full system, then a lot of your computational power goes waste in resolving these faster variables. Okay? Because you need to do simulation on a much smaller time scale to be able to see what the statistical properties of these are. But the theory tells us that as epsilon goes to 0, the slope variable xt can be shown to converge. In that particular case, the particular example that I'm looking at, the slope variable xt actually converges to the Monstein-Goldbeck process, which is what I had set up in the previous example itself. Again, it's sort of, this model fits into our general framework. Here, the assumption again is that this the OU process to which my slope variable converges is unobservable. Okay? There are some parameters, lambda and sigma, that need to be estimated but that estimation is based on data that's coming from the full multi-scale system, or the slow variable in the full multi-scale system. So the x here is analogous to the y epsilon, the approximated process, and the only process to which it converges is my unobservable process xt. So again here, experimental studies, some numerical experiments show us that here the conditions are that this alpha has to be between 0 to 2. So to say that the bias in the parameter estimates due to the indirect observability is of the order epsilon squared over delta. In the previous case we had epsilon over delta. Here we have epsilon squared over delta. Okay, so we have to choose delta going to 0 such that it's of course slower, but it's slower with these conditions. Okay? Slower than epsilon squared. Alright, so just let's look at some numerical results here. So if I choose delta to be epsilon to the power 0.5, again the good regime, my parameter estimates error converge to 0. If I choose it to be epsilon squared, that is the case when I would have an order 1 error, because the bias here is epsilon squared over delta. Okay, so again, that is what I see numerically. And then if delta equals epsilon to the power 3, which is sort of outside this optimal regime, then I see that the errors actually go up. Okay? Now, this problem is also seen in molecular dynamics in when you look at biochemical reaction networks. So biochemical reaction networks would be a system of ODEs, where some of the reactions, some of the reactions are happening on a much faster time scale, and some other are happening at a much slower time scale. So the rate constants for these reactions could be very different. There could be sort of time scale separation between if you sort of track the concentration of these different chemical reactants, and then if you're only interested in what the slow variables or the statistical properties or the asymptotic properties of the slow variables are, then you need to sample under the conditions I set forth in this study, which is that you cannot sample very frequently. Okay, so this is the counterintuitive notion. That you need to throw some data to be able to get estimates which are unbiased, which have lower bias in them. Okay? So more data is not always good. Alright, so I'm now going to jump, so this is just to sort of compare the slow variable versus the OU process numerically, but I think I'll skip this. I'll sort of quickly comment. So this is what sort of indicates that there is small scale difference in the two processes. So this is the correlation function for my OU process. So my stationarity I extended sort of symmetrically on the other side, so it is not differentiable at lag 0, whereas the correlation function for the slow variable in my triad model is also sort of concave down and it's differentiable. So it is similar to the case of the smooth OU process in certain sense. Alright, so let's now Alright, so let's now move to the stochastic volatility model. So I very briefly motivated it in the beginning of the session, but let me sort of go over it. So stochastic differential equations have sort of taken center stage when it comes to capturing the dynamics of financial time series or modeling the randomness in the financial time series. Especially over the last decade or two, with advancement in technology, with computerization of the exchanges and trading, there is more and more data available, right? So there is high frequency data available, and that allows us to sort of estimate the SDE parameters in a much more reliable manner. So in the current times, we have tick by tick data for the stock prices or other financial asset prices. It's available at like 10 to the power, at like microseconds and even shorter time scale, But again, sort of the cautionary note here is that it's not always good to have more data to estimate these models. In fact, even in high frequency finance, there is this notion of microstructure noise. That is, if you sample your financial time series very frequently, then there are these observational errors which kind of mess up your parameter estimation. That is not what I will be touching upon, but I'm sort of presenting a slightly different study here. It fits into the indirect observability context, but we'll get to that. So just to sort of mention, Black-Scholes, so Fisher-Black, Myers-Scholes, back in 1973, they devised this model which allows one to price financial instruments called derivatives. So derivatives are these contracts which derive its value from other financial assets. Okay? They are also sort of popularly called the weapons of mass destruction because there is too much reliance on these, and sometimes these are not very well understood. The pricing of these financial instruments are not very well understood. But the Black-Scholes model, and Merton also did some work on it. In fact, they got Nobel Prize for this work. They basically set a framework within which they were able to price the derivative, and they actually derived a partial differential equation which the option price or the derivative price satisfies, and that partial differential equation is nothing but the differential equation, and therefore they were sort of able to solve the pricing equation for that, or arrive at the price of the derivative. But what it assumes is that the underlying stock price ST. So I said the derivative derives its price from some underlying asset. The underlying asset, let's say it is stock price. It can be anything. It could be weather. It could be commodity price, or any other asset prices. So the stock price ST was assumed to follow geometric Brownian motion. So geometric Brownian motion is can be represented as a stochastic differential equation where the parameters for the drift and the diffusion are assumed to be constant. Okay, so that is a strong assumption, and it has been shown to be a very strong assumption, and it has been sort of studied that Black-Scholes framework doesn't capture sort of all the stylized features which is observed in the price, in the asset prices. Some of them being that the volatility, which is assumed to be constant, is in fact not constant. That is a very, very strong assumption here. So stochastic volatility model actually extends the Black-Scholes model to a framework where you assume that not only is the stock price stochastic, but its associated volatility is also stochastic. So it becomes a two-dimensional stochastic differential equation. Okay? Now the challenge lies in the following: that the volatility process, which is assumed to be stochastic. So let me actually move to the next slide because you will probably see the equations. So the first equation sort of represents the price. Strictly speaking, it represents the log of the price. But just consider it to be sort of the signal, and the sigma squared in the geometric Brownian motion is assumed to be constant, so independent of time. So here you would just see sigma. But in the stochastic model, it is assumed to be stochastic, and we consider the following, that it follows the following model process. Okay. Challenge is that the volatility process is actually not observable in the market. There is no volatility market. I mean, there are proxies for it. There is something called an implied volatility, which is observable, only a proxy to this true process sigma. And there is something called realized volatility or the historical volatility, which is computed from my process X, which are the stock prices. So given that, so now the problem in indirect observability here is that I want to estimate the parameters for the second equation here, which is my volatility process, but the only thing that I observe is the signal X or the stock price X. Okay. What is the proxy for sigma that I would consider here? The proxy that I would consider is the following. So I said that there is something called historical volatility, So the historical realized volatility, given that I have, let's say, 20 years of data, daily data for my or intraday data. Every 5 minutes I have my stock price. Suppose I collect all that in the last 10 years, 20 years. Then based on that observed stock price, I can define the following, which is basically the sum of, it's sort of this, the variance estimate, right? It's the variance estimate for the log returns, okay? This can be shown is this y epsilon t can be shown to be an estimate for my sigma t. So as epsilon goes to 0, okay, this process y epsilon t, which is my realized volatility, based on only the observed stock price, can be shown to converge to this true volatility process, which has been assumed and rightly assumed to be unobservable. Right? So now the problem boils down to observing this process y epsilon and estimating the parameters in the equation for sigma. So this particular framework is very much outside the general frameworks that I introduced in the beginning, because there I had the Gaussian, that the true process which is unobservable is Gaussian. Here, the process sigma, so this is sort of a popular process in itself, very well studied, it's called the Feller square root process. This can be shown, it's non-Gaussian. The distribution for the process sigma is known to be non-centrally chi-squared. It's stationary, with the stationary distribution being gamma, so there are some well-known properties of it, but it's non-Gaussian. So the idea that we are trying to explore is, one, can we extend our general framework to include non-Gaussian processes? And second, idea that we're trying to explore numerically is that do we see this whole issue of indirect observability or the sampling or the subsampling issue, which is that if I sample very frequently from my process y epsilon, can I get estimators for the process sigma squared? Well, so I've stated this. This is the indirect observability. This is what the problem is sort of boiling down to. I observe discrete samples from y epsilon t, and I'm estimating my stochastic process sigma squared t. All right. So I think I'll skip this. It's just some sort of notation here. The idea really sort of lies in here. So of course, for the numerical results, we have set up a simulation example, which is that I assume certain parameter values for the process for sigma squared, and you simulate the trajectories for x and sigma squared. So this is the true trajectory that has been simulated from the process sigma squared. Okay, this is the constructed data from observing only the signal x. Okay, so this is the realized, this is my y epsilon, this is my x. So what we notice here, in contrast with the OU process and the smoothed OU process, the smooth OU process would have had continuous trajectory. Difference was smooth trajectory. Here, in the approximating process, there is more noise, there is more fluctuation. Okay, so it's kind of a different example than the previous one. But again, the idea is that if I sample very frequently from this process and I intend to estimate parameters for a stochastic process whose trajectories look like this, then I may not get back. I mean, I'm going to make the bias or the errors in the parameter estimators are going to be high, which is what happens. So here I've just sort of stated what those parameter estimators are. Again, the idea is that those parameters which appear, these three parameters are the ones that appear in my volatility process. Those can be represented as some functions of covariance, some functions of the moment estimates. Okay, either the first order moment or the second order moments. Okay, so the covariance, again, it's the covariance which is sort of critical in terms of determining the asymptotic properties for these estimators. So if I'm able to establish that these moment estimators, which are defined here, I'm able to consistently estimate these, then I'm able to sort of show consistency of these estimators for the volatility process as well. Okay, so I sort of end the presentation here. The conjecture here is that the order of the bias in the parameter estimators here is epsilon over delta. Okay, it's sort of similar to what we had in the first example of the Ornstein-Milgret process being unobservable and the smoothed Ornstein-Milgret process being the observable. So as epsilon over delta, so now here the numerical results that I presented is that I fix my window. So this is again a practical example. Let's say I take the last 20 years of stock price data. Given that one data set for stock price, from that I compute my historical volatility time series, or the y epsilon, for a fixed epsilon, and then if I change my sampling time step, what is the impact on the parameter estimators? I see that if I sample less frequently from my historical volatility time series, then I can get back my true estimates. Or to say that the parameter, the errors in the parameter estimates are of order 1 over delta, even in this case. Okay? So we are trying to sort of extend our general framework to include non-Gaussian processes, and then this particular example will fit very well in that. And also to sort of establish some of the hypotheses that we had for the general framework. For instance, the bounds on the L4 norm or the L2 norms between the processes and so on. So what is the order of convergence? Once we're able to establish that, we'll be able to sort of test numerically that in fact that the order of bias is epsilon over delta, okay, due to the indirect observability. So that I think is where I end. Just concluding, so we put forth a formal mathematical framework to study estimation when the observations are actually coming from an approximating process and not fixed process, which is being estimated. We've derived some conditions to ensure asymptotic consistency of the parameter estimates. We considered some sort of prototypical models where exact results could be found out, and the results were also tested on the multi-scale system, the additive triad system that we had, and then extended to the stochastic volatility case. All right. Thank you so much for your attention. So part of this research was done while I was a postdoc at Mathematical Biosciences Institute with Robert Asymptotic and Vidya. The work has been presented in papers below, so there is interest. Please, thank you so much.